Welcome! Today, we're tackling LeetCode problem number 383, titled Ransom Note. This problem challenges us to determine if a given string, representing a ransom note, can be constructed using the characters from another string, representing a magazine. It's a fun and practical problem that tests our understanding of string manipulation and character frequency counting. Let's dive right in. The problem asks us to determine if we can construct a given string, ransom note, using the letters from another string, magazine. Here's the catch: each letter in magazine can only be used once. For example, if the ransom note requires 2 occurrences of the letter A, the magazine must have at least 2 A's available. Both strings consist of lowercase English letters, and their lengths can go up to 100,000 characters, so our solution needs to be efficient. The output is a Boolean value, true if it's possible to construct the ransom note using the letters from magazine, and false otherwise. Let's go through a few examples to clarify this further. In the first example, the ransom note is A and the magazine is B. Here, the letter A that we need for the ransom note isn't found in the magazine. Since there's no match, it's impossible to construct the ransom note, so the output is false. Now, in the second example, the ransom note is AA and the magazine is AB. While the magazine contains one A, it doesn't have the second A needed to complete the ransom note. Again, the construction isn't possible, so the output is false. Let's move to a scenario where the construction is possible. In the third example, the ransom note is AA and the magazine is AB. Here, the magazine contains 2 A's, which is exactly what we need to construct the ransom note. Since the available letters in magazine are sufficient, the result is true. Now, let's consider a few constraints and edge cases. First, if the ransom note is longer than the magazine, it's impossible to construct, and the result will always be false. If the ransom note is empty, the result is always true because no letters are needed. On the other hand, if the magazine is empty but the ransom note isn't, the result is always false. Finally, when the ransom note and the magazine have the exact same letters and the same frequencies, the result will be true. To solve the ransom note problem, the goal is to determine if the ransom note string can be constructed using characters from the magazine string, keeping in mind that each character in magazine can only be used once. This essentially means we need to verify if all characters in ransom note exist in magazine with at least the required frequency. A straightforward way to approach this would be the brute force method. The idea here is to iterate through each character in ransom note and check if it exists in magazine. If the character is found, we remove it from magazine to simulate its usage and continue checking the next character. If any character in ransom note is missing, we return false. While this method is simple to understand, it's highly inefficient for large inputs because for every character in ransom note, we may need to scan the entire magazine. This results in a time complexity of O, n asterisk m, where n is the length of ransom note and m is the length of magazine. Additionally, creating a mutable copy of magazine adds an O, m space overhead. These inefficiencies make the brute force approach impractical for larger datasets. A more efficient method is the frequency counting approach. Instead of checking characters one by one, we can reduce the problem to comparing the frequency of characters in ransom note and magazine. The idea is to count how many times each character appears in both strings and ensure that for every character in ransom note, magazine contains at least the same number of occurrences. To implement this, we can use the counter class from Python's collections module to easily count character frequencies for both strings. Then, we compare the counts to make our decision. This approach processes each string only once, giving it a time complexity of O, n plus m, where n and m are the lengths of ransom note and magazine, respectively. In terms of space, it's quite efficient as we only need to account for 26 lowercase letters, resulting in constant space usage. While this method is slightly more memory intensive due to maintaining 2 frequency maps, the overhead is small. Another optimization involves using a single pass approach. Here, we decrement the frequency of characters in magazine as we verify ransom note. If any characters count drops below 0, we know that ransom note cannot be constructed. This method also runs in O, n plus m, time and uses constant space, but it requires extra care to avoid implementation errors like off-by-one mistakes in frequency adjustments. The frequency counting approach stands out as the best strategy for this problem due to its combination of efficiency and simplicity. With a time complexity of O n plus m, it's well suited for handling large inputs, and using counter ensures that the implementation is concise and easy to understand. While the optimized single-pass approach is slightly more memory efficient, it comes with added complexity, making it more error-prone and less beginner-friendly. The brute force method, on the other hand, is too slow to be practical for larger inputs. The key insight here is recognizing that this problem reduces to comparing character frequencies, a task that is efficiently handled using hash maps or Python's counter. Additionally, since we only deal with 26 lowercase letters, the frequency map remains small and space usage is constant. By choosing the frequency counting approach, we strike a balance between clarity, performance, and maintainability. Although the single-pass method saves some space, its complexity introduces potential for subtle bugs. This makes the frequency counting approach the ideal solution for solving the ransom note problem effectively while minimizing the likelihood of implementation errors. To solve this problem, we need to determine if the string ransom note can be constructed using the characters from the string magazine. Each character in magazine can only be used as many times as it appears in the string. For instance, if ransom note is ob and magazine is ba, the answer is true because all the characters in ransom note can be found in magazine and in sufficient quantities. To approach this, we start by understanding the inputs and outputs. The inputs are two strings, ransom note and magazine, and the output is a Boolean value indicating whether the construction is possible. A key observation here is that each character in ransom note must appear in magazine with at least the same frequency. If any character in ransom note exceeds its frequency in magazine, the task becomes impossible. The approach we'll use involves counting the frequency of characters in both strings and comparing these counts to determine if construction is feasible. The algorithm can be broken into three main steps. In step 1, we initialize a frequency map, which is essentially a hash table, to count how many times each character appears in magazine. This is done by traversing magazine character by character and updating the count of each character in the map. In step 2, we verify if ransom note can be constructed by traversing it character by character. For each character, we check if it exists in the frequency map and if its count is greater than 0. If it does, we decrement the count, representing that we've used this character. If it doesn't exist or its count is 0, we immediately return false because the construction is no longer possible. In step 3, if we process all characters in ransom note without issues, we return true, indicating that the construction is successful. This algorithm is efficient because we traverse each string only once, giving us a time complexity of O, m plus n, where m and n are the lengths of magazine and ransom note. Additionally, using a hash table allows for constant time operations, and the early exit condition ensures unnecessary computation is avoided. The key data structure we use here is a hash table, or dictionary, to store the frequency of each character in magazine. This is an ideal choice because it allows us to perform lookups and updates in constant time on average. There are also several edge cases we need to consider. If ransom note is empty, we can immediately return true since no characters are needed to construct it. Conversely, if magazine is empty while ransom note is not, we return false because we don't have any characters to work with. Another edge case arises when ransom note contains characters that don't exist in magazine. In such cases, the result is false. Finally, if the two strings are identical in both characters and frequency, the result will be true because the construction is trivially possible. The algorithm implementation begins with counting character frequencies in magazine using Python's collections counter. This simplifies the process of creating our frequency map. Once we have the frequency map for magazine, we start processing each character in ransom note. For every character, we check its count in the map. If the count is greater than 0, we decrement it to signify that the character has been used. If the count is 0 or the character is missing in the map, we return false immediately since it's impossible to construct ransom note. After processing all characters in ransom note, if no issues arise, we return true to indicate that the construction is successful. Regarding complexity, we achieve O, m plus n, time complexity, as counting characters in magazine takes O, m, and traversing ransom note takes O, n. The space complexity is O, 1, in terms of additional space, as the hash table stores at most 26 entries for lowercase English letters. This ensures the algorithm is both time efficient and space efficient, making it suitable for large inputs. Let's go through an example to see the algorithm in action. Suppose ransom note is ob and magazine is ba. First, we count the characters in magazine, resulting in the frequency map, B1, 2. Next, we process the characters in ransom note. For the first it's found in the map with a count of 2, so we decrement the count to 1. For the second it's found again, and the count is decrement to 0. Finally, for B, it's found with a count of 1, and the count is decrement to 0. Since all characters in ransom note are matched successfully, we return true. This example demonstrates how the frequency map ensures efficient tracking of character usage, and the early exit condition minimizes unnecessary work. Overall, this algorithm is a robust solution for the problem, handling all edge cases effectively while maintaining optimal performance. This solution employs a frequency count approach using Python's counter from the collections module. The goal is to determine if the string ransom note can be constructed using characters from magazine, given that each character in magazine can only be used as many times as it appears. Explanation. 1. Frequency count. Counter, ransom note. This creates a dictionary-like object where the keys are characters from ransom note and values are their respective counts. Counter, magazine. Similarly, this creates a frequency count for magazine. 2. Check character availability. We iterate over the characters and their counts in ransom_count. For each character, we compare its count in ransom note, ransom_count, char, with its count in magazine, magazine_count, char. If magazine has fewer occurrences of any character than required, we return false immediately. 3. Return result. If all characters in ransom note can be matched with sufficient frequency in magazine, the function returns true. This approach is efficient because the counter creation has a time complexity of O, n plus m, where n and m are the lengths of ransom note and magazine, respectively. The iteration over ransom_count is proportional to the number of unique characters in ransom note, which is usually much smaller than the total string lengths. Edge cases. If ransom note is empty, the function should return true since no characters are needed. If magazine is empty and ransom note is not, the function should return false. If ransom note contains characters not present in magazine, the function will correctly return false. Overall, this is a clean and efficient solution with a time complexity of O, n plus m, and space complexity of O, u, where u is the number of unique characters in the input strings. This is the Java implementation of LeetCode problem number 383, ransom note. The logic matches the Python version, using a hash map to count character frequencies from the magazine string. For each character in the ransom note, the code checks if enough occurrences are available in the magazine. If not, it returns false. Key differences include explicit type declarations and the use of Java collections, such as hashmap, instead of Python's counter. This approach ensures efficient character counting and lookup. To solve LeetCode problem number 383, ransom note, we need to determine if we can construct the ransom note string using characters from the magazine string. Let's analyze this through a few examples. In the first example, the ransom note contains the letter A, and the magazine contains the letter B. Since our task is to check if the magazine contains all the characters needed for the ransom note, we start by counting the frequency of each character in both strings. Using Python's counter, we find that ransom_count is A1 and magazine_count is B1. Next, we compare the counts. The ransom note requires 1 A, but the magazine has 0 A's. Since the magazine does not have enough of this character, we can immediately conclude that the ransom note cannot be constructed. The output for this example is false. Now, in the second example, the ransom note contains 2 A's, and the magazine contains 2 A's and 1 B. To determine if the ransom note can be formed, we again count the frequency of characters in both strings. Here, ransom_count is A2, and magazine_count is A2 B1. Next, we compare the counts for the characters in the ransom note. For the character A, the ransom note requires 2, and the magazine also has exactly 2. Since the magazine has sufficient occurrences of A and there are no other characters in the ransom note, we can conclude that the ransom note can be constructed using the magazine. The output for this example is true. In the third example, the ransom note contains 3 characters, A, B, and C, each appearing once. The magazine contains 2 A's, 2 B's, and 2 C's. To check if the ransom note can be formed, we calculate the frequencies of each character. Here, ransom underscore count is A1, B1, C1, and magazine underscore count is A2, B2, C2. We then compare the counts for each character in the ransom note. For A, the ransom note requires 1, and the magazine has 2. For B, the ransom note also requires 1, and the magazine has 2. Similarly, for C, the ransom note requires 1, and the magazine has 2. In all cases, the magazine has enough of each character to meet the requirements of the ransom note. Therefore, the ransom note can be constructed, and the output is true. The examples demonstrate key observations about the algorithm. It uses Python's counter to efficiently calculate the frequency of characters in both strings. Then, it iterates through the ransom underscore count dictionary, checking if each required character is available in sufficient quantity in the magazine. If any character is missing or insufficient, the function immediately returns false, avoiding unnecessary computation. This makes the algorithm efficient, with a time complexity of O, n plus m, where n is the length of the ransom note and m is the length of the magazine. This approach ensures both correctness and efficiency, as we've seen through the examples. To analyze the time complexity of this solution, we start by breaking it into 2 main steps. First, we count the characters in both the ransom note and the magazine using the counter class. Constructing ransom underscore count requires iterating through all the characters in ransom note, which has a length of m, taking O, m, time. Similarly, constructing magazine underscore count involves iterating through all characters in magazine, which has a length of n, taking O, n, time. Together, this step has a total time complexity of O, m plus n. Next, we iterate through the ransom underscore count dictionary. The for loop processes all unique characters in ransom note, and for each character, we perform a dictionary lookup in magazine underscore count. Dictionary lookups are O1 on average, so the complexity of this step depends on the number of unique characters, denoted as U. In the worst case, where all characters in ransom note are unique, U is proportional to m, making this step O(m). Thus, the overall time complexity for this part of the process is also bounded by O(m). Combining the 2 steps, we see that the total time complexity of the solution is O(m plus n), where m is the length of ransom note and n is the length of magazine. Now, let's examine the space complexity. The primary contributors to space usage are the 2 counter objects, ransom underscore count and magazine underscore count. The ransom underscore count object stores the frequency of each unique character in ransom note. In the worst case, if all characters in ransom note are unique, the space required is proportional to the number of unique characters, denoted as U. Here, the worst case is O(m). Similarly, magazine underscore count stores the frequency of each unique character in magazine, which requires O(v) space, where v is the number of unique characters in magazine. In the worst case, this is O(n). Together, the space used by these 2 objects is O(m plus n). Additionally, the algorithm uses a constant amount of extra space for variables like char and count during iteration. Therefore, the total space complexity is also O(m plus n). To understand the efficiency of this approach, let's compare it to a naive solution. In a naive approach, we would iterate through each character in ransom note and check its occurrence in magazine by scanning magazine repeatedly. This would result in a time complexity of O(m*n), as each character in ransom note triggers a full scan of magazine. However, the naive approach has a space complexity of O(1), because it doesn't use any additional data structures. In contrast, the current approach significantly improves time complexity to O(m plus n) by leveraging the counter class for efficient frequency counting and dictionary lookups. This improvement does come with a trade-off in space usage, as the space complexity increases to O(m plus n) to accommodate the counter objects. When analyzing the best, average, and worst-case scenarios, the best case occurs when a mismatch is found early in the for loop. For example, if the first character in ransom note is not present in magazine, the loop exits early. Even in this case, the time complexity remains O(m plus n) due to the cost of constructing the counter objects. In both the average and worst-case scenarios, all characters in Ransom Note are checked, and magazine is fully processed, maintaining the same overall complexity of O, M plus N. To solidify our understanding of why this solution is O, M plus N, let's look at the mathematical justification. The use of counter ensures that the frequency counting operations are linear with respect to the size of the input. Specifically, iterating through Ransom Note takes O, M, time, and iterating through magazine takes O, N, time. During the for loop, we perform dictionary lookups for each unique character in Ransom Note. These lookups are O1 on average because hash map operations are constant time. The loop itself iterates over at most U unique characters, where U is less than or equal to M. This means the complexity of the loop is bounded by O, M. When we combine the O, M, for Ransom Note, O, N, for magazine, and O, U, for the loop, where U less than or equal to M, the overall time complexity remains O, M plus N. This balance between the linear operations and efficient lookups explains why this approach is optimal for solving the problem. When tackling the Ransom Note problem, there are a few common mistakes to watch out for. First, it's important to account for character frequencies. It's not enough to simply check if a character exists in the magazine. Instead, you need to ensure that the magazine contains each character from the Ransom Note the required number of times. For example, if the Ransom Note is AA and the magazine is A, the solution would fail if you only check for the presence of the letter A without considering its frequency. Another common pitfall is using an inefficient search approach, such as iteratively searching for each character of the Ransom Note in the magazine. This can lead to an O, N squared, time complexity, which is unnecessary. A better approach is to use a frequency counter or a dictionary to keep track of character counts. Modifying the input strings directly is another mistake to avoid, as it can lead to unexpected side effects, especially in languages where strings are immutable. Edge cases also require careful handling. For instance, an empty Ransom Note should always return true, while an empty magazine should always return false. Finally, avoid over-optimizing too soon. While it's tempting to use complex data structures like heaps or tries, they can make your code harder to read without providing significant benefits for this relatively simple problem. Understanding the broader context of this problem can be very helpful in interviews. At its core, this problem is a variation of the subset problem, where the goal is to determine if one collection is a subset of another based on specific criteria, in this case, character counts. The optimal solution involves using a frequency counter, such as collections counter in Python or a hash map in other languages. This approach achieves an efficient O, N plus M, time complexity, where N and M are the lengths of the Ransom Note and magazine, respectively. During interviews, it's important to communicate your thought process clearly. For example, you should clarify edge cases, such as how empty strings or case sensitivity are handled, and explain why you've chosen specific data structures. Hash maps are particularly effective here because of their average O1 lookup time. Be prepared for follow-up questions as well. Interviewers might ask how you would handle variations like a very large magazine, potentially processed as a stream, or how the solution would change if characters were associated with weights instead of counts. Additionally, exploring related LeetCode problems can deepen your understanding. For instance, valid anagram focuses on character rearrangement, while group anagrams extends this concept to clustering strings. Problems like first unique character in a string or valid parentheses also involve character-based operations, making them great practice for honing similar skills. There are alternative approaches to solving the Ransom Note problem, though they often involve trade-offs. One option is a sorting-based approach, where you sort both the Ransom Note and magazine strings and then compare them. While this is straightforward to implement, its time complexity of O, N log N plus M log M, makes it less efficient than using a frequency counter for large inputs. Another alternative involves bit manipulation, which could theoretically work if the problem were restricted to lowercase English letters. This method uses bit masks to represent character presence, but it falls short here because it doesn't account for character frequencies. It's also harder to generalize, making it impractical for this problem. A more realistic variation involves handling streaming input, where the magazine is processed as a continuous stream. In this scenario, you could use a sliding window or maintain a running frequency count, which allows you to dynamically check if the Ransom Note can still be constructed at any point. However, this approach introduces additional complexity, particularly in managing memory usage for large streams. Each of these methods highlights different ways to approach the problem, but the frequency counter remains the most efficient and practical solution for most scenarios. Great work! We've wrapped up the ransom note problem. In this lesson, we explored an efficient hash map-based solution and reviewed its time and space complexities. Remember, problems like this are excellent for sharpening your skills with hash maps and string manipulation. Thanks for joining me. Be sure to like and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!